on all of that quantity and raise it to the fifth. This is a notation thing. Okay? We need to all understand this is the way it is. So when we want to write this, we actually just write it that way. So when we were doing like sine squared x in pre-cal, we really meant sine x squared. So what's important for us is to understand the order in which we would do this. If I asked you right now to take a value of x and plug it in, it would go here, right? And so you'd figure out what that is, and then what would you do? You would take sine of it, right? And then what would you do? Raise it to the fifth power. Okay, so that's the order in which things happen here. All right, so take a look at that capital M function. And what you're asked is to try and decompose that. In other words, come up with three functions such that that function is this composition. It's f of g of h of x. Okay, so what the heck do they want here? They want us to come up with three functions, f of x, g of x, and h of x. And they want us to come up with these functions in a way that when we start plugging certain functions into certain functions and keep doing that, we wind up with this at the end, right? So what is the order? What does this notation here mean? Like what function is on the outside? What's the last function? When you see this, what's the last function on the outside? The f. What's the one in the middle? G and then h. So this actually means you're going to take f, and inside of f you're plugging g, and inside of g you're plugging h of x. Okay, so that's what that notation means. So let me help you try and do this. The way I'm going to do it is I'm going to work backwards. I'm going to look at this expression, which is actually this, and I'm going to ask myself, what's the last thing that happens? What did we say the last thing that happens was? We're raising it to the fifth power, right? Okay, so I'm going to make my outer function, my f function, I'm going to raise it, I'm going to make it something that raises things to the fifth power. Okay? Now, if I've taken care of that, then what's the next level in? What function is the next level in? The sine function, right? So my middle function needs to take sine of something. And then what would that inside piece be? The x squared plus 1. So let's see if you can kind of unwrap this now. If I tell you to take this function and plug it into that one, you would get sine of what? X squared plus 1. And then if I tell you to take that answer and plug it in there, what would you get? All of that to the fifth power, right? Does that make sense? Do you want another example? Let's do another example. How about I give you this one? So that was the answer right there, okay? So I'm going to make up another one. Capital M of x equals the square root of natural log of, I'm going out on a limb here, square root of the natural log of sine of x squared. And what I want you to do here is break this down, decompose it into f of g of h of k of x. So I want you to actually break it down into four functions. F of g of h. I didn't use I, right? Or j? I don't know why I went straight to k. I know I didn't use I like to keep I for the imaginary number, but so let's see. F is the outer function, g is the next one in, h is the next one in, and k is the inside function. So again, I like to work my way from the outside in, but I'm not going to. Omar's going to. Where's Omar? Okay, Omar, when you look at this, what's the last thing that happens? Square root it. Now, does everyone understand what I mean by that? Like if you plug in an x, you're going to first square it, then you're going to do sine, then you're going to do natural log, and then at the end you're going to square root it. So the square root is the last thing that happens, so that's going to be my outer function f. Square root of what? X. Okay. Now, Elijah, what's, if we've taken care of the square root, what's the next function inside that? Natural log, right? So we'll just do natural log of x. Owen?
Next is sine of x.
Sine of x. And finally, Danielle. Where's Danielle? Pardon? Diaz. No? That's you. Oh, that's right. So what's the inner function? Sorry? X squared. All right. So do y'all see it? If x squared goes into here, we get sine of x squared. If that goes into here, we have natural log of sine of x squared. If that goes into here, we have the square root of natural log of sine of x squared, which gives you back that. So for us later, being able to decompose is going to make your lives so much easier if you can do this decomposition. Yes?
Do you prefer the f of x, for example, f of x equals parentheses x to the 1/2?
Either way will work. Yep, yeah. So the question is this, do I prefer this? Either one will go. I mean, we're good. All right. Yes?
So you basically go from the outside.
Outside in. Yep. Now you could go from the inside out, like this way, but later on when we're going to be trying to do something called the derivative, we're actually going to work from the outside in. So we may as well start writing them down that way so that we're kind of already going in that direction. Okay. Do you want another one or do you want to leave it alone? No. All right, you okay? We move on. All right. So now I'd say that the class is going to officially begin. Like the calculus is going to begin. All right. So, you know, there's 3 calculus courses in the calculus sequence. Cal 1, Cal 2, Cal 3. Some schools have 4 calculus classes, but it's not that they have more, they're doing more. It's either you either have 3 4-hour classes. This is a 4-hour credit, right? 4-hour credit. Or you do 4 3-hour credits. So the calculus sequence should be a total of 12 credit hours. So all calculus, all of it, every single piece of it, has at the heart of it the idea of the limit. Okay? So if I were to draw like all the different subjects in calculus, put them all up here, they would all branch back down to this one topic right here, the limit. So very, very important. And I think what's nice about the limit, at least initially, is that we can look at it very visually. And then it'll become algebraic and you won't like that very much. But you know, at least at the beginning we can look at it from, you know, using our eyes and pictures, and we seem to do better with that, right? When we can visualize things. All right, so right now what I'm going to do is I'm going to show you a graph, and I want you to look at the behavior of this function at the value x equals 2. All right, so I want you to focus your attention on what's happening at x equals 2. So can somebody tell me, or not somebody, how about David Garza? David? Okay, David, I'm going to ask you, what is this from looking at that picture? What is f of 2? 8. Okay, so all you're doing is you're saying, hey, look, this is a college algebra problem, right? He's asking me to go to an x value of 2 and look at where I have graph. So you look up and you say, oh, there's the point on the graph, and that's at 8, and we're done. That is college algebra, right? Okay. Now what I'd like to do is I'd like to not look at what's happening at 2. I want you to look at what's happening near 2. So imagine that I'm now going to cut the middle, wrong way. I'm going to hide that from you, all right? So you no longer get to see what's happening at 2. And I want you to just focus on what's happening near 2, all right? So let me ask Herman. Where's Herman? Okay, Herman. Imagine that you're walking along this graph, okay? You see yourself walking along this graph? Yes? Okay, you're walking, it's like a little roller coaster, you're going, right? And the height that you're at is changing, right? So right now you're at like 5, you go up a little more, you're at 6, 7. What's happening as you get closer to an x value of 2, what is your height approaching? It's getting closer to 8, isn't it? It's getting closer to 8. Now, I'm not asking you to tell me what's happening at 2. I'm saying near 2, right? Near 2. So from the left side, it appears that we're approaching 8. So we're a little under 8, but we're getting closer to 8. Yeah? Okay, so what about, is it Jamie? From the other side, where's it? From the other side, if you're walking along here, right? You're going here. You're higher than 8 right now, right? But then you come over this little hump and you come back down, and what are you approaching? You're approaching 8, right? So from both sides, from the left side and from the right side, your function appears to be approaching 8 from both directions. And at 2, what was it? It was 8. So it's like everything is beautiful in this problem, right? Everything is just working out perfectly. If we reverse the window and we say, that's your college algebra problem. Don't look at anything but 2, it's 8, right? That's college algebra. And if you say, now put your calculus goggles on, now you say, forget what's happening at 2 and look at what's happening near it. So I'm going to just show you one more quick little animation. As we come in from the left-hand side, I guess I have to show it. If we come in from the left-hand side, as we approach 2, notice that the y value in purple is getting closer and closer to 8, right? Okay, as we come in from the other direction, as our x value approaches 2 from the right-hand side, our y value up there is approaching 8 also. Okay? Everything's great in this problem. Different problem. Everyone take a look at it. Just focus on this picture. Don't worry about all that, okay? Let's see. Is it Lanissa? Yes, did I say it okay? Okay. Lanissa, you get the algebra question. So what is f of 2? So I'm asking you to ignore everything except what's happening at 2, right? And can you tell me what's happening at 2? What's the function's value?
4.
So you're getting 4 from this.
Oh.
What about up here? So which one is it? How do you know which one it is?
Would be 8 because that one's a hole.
Yeah, this one's a hole, right? And this one's a solid dot, so it's going to be 8. All right. Okay, college algebra, done. All right, now we're going to go and do it from the calculus perspective. We don't get to look there anymore. And Marcus, sir, all right, I remembered you. I looked right at you, right? Marcus, what is this function's value approaching if you come in from the left-hand side? 8 also, right? So you're walking along there. Does everyone see that? Walking along, coming in from the left-hand side. The y-coordinate is getting closer and closer to 8, right? Okay. Ian, where's Ian? Ian, you get to come in from the right. Okay, so what do you see? What do you see as we come in from the right? What does it look like the function's value is approaching? 4. Do you all see that? See, this time we come in from the right, our y-coordinate goes up. It's up at like 5.477. And then as we get closer and closer to 2, coming in from the right, it looks like it's diving back down to about 4, right? Okay, so what was happening at 2, right? At 2 it was 8. From the left it was 8, and from the right it was 4. So it's like of the three things that we're looking at, two of them were the same and one of them wasn't, right? All right. Jesse, the algebra problem. What is f of 2?
It can't be neither 4 or 8.
Okay, so it's not these because there's holes there, right? But there is something there. What is it? 6, right? So for this graph, we are covering up everything, and we're saying, look, at 2 we look up and down. Where do we have a dot? We have it at 6, right? So the answer to the algebra problem is 6. And David, how about from the left side? If you approach 2 from the left side, what is your function's value approaching? Here we go. 8, right? So we're headed up to 8. Do we ever get to 8? We never actually get there, but we're talking about, when we're talking about this idea of a limit, we're talking about like what things are getting close to as we get closer to other things, right? That's this weird concept. And then, that was David. Arturo? Okay, from the right, what do we got? Gets closer to 4, right? Everyone agree? So, let me see if, I've already forgotten who I called on. Hold on. I know that. 4, we got 4 from the right, right? We got 8 from the left, right? That's what you did? Okay, there we go, sorry. And then you got 6 at 2. So now this is an example where none of them matched, right? Like from the left we get one thing, from the right we get something else, and then at that point we get something completely different. All right? Okay. So this is x is 0, this is x is 1, this is x is 2, 3, and 4. I don't know if you can see that. So this is x is 2, and is it Salo? Am I saying that right? Yes. Okay. You get the algebra question. What's happening at 2? So I'm asking you, go to 2 and tell me the value of the function. So what does this little open little thing mean? What does that open circle mean? There's nothing there. There's a hole there, okay? So I'm asking you to plug 2 in. You're looking for the graph, and you're seeing a hole. And you're not seeing any other points anywhere else, right? So what is this function at 2 then? There's no function, right? So we say it's undefined. It's undefined. Oops, undefined. It's undefined at 2. All right? Now, how about from the left? Is it Oya?
Yes.
Am I saying that right?
Yeah.
Man, you know, in my class yesterday, there was like 8 students where I was saying their names exactly the way they appeared on paper, and I was off on every single one of them. So I'm doing good today. I think I'm averaging out to be just okay. All right, Oya. Oya. Okay, Oya. From the left, what is this function approaching? I think it's going to be hard to see. It's hard to tell. So can you kind of guess? Negative 2 is down here. So we're approaching here from the left.
Oh, so it'd be close to 1.
Yes, somewhere in there, right? Let's have the computer help us so we can kind of see it. So from the left, here we come, here we come, here we come. Looks like it's, I don't know, like negative 0.25-ish, somewhere around there? Okay. And then what about from the right? Marissa? Yeah, from the right, what do you think? Same, like about the same thing, right? So it's like from here, it's the same as from here, okay? So here's an example where we're coming from the left and the right, and we get the same answer, right? But actually, at the point 2, it's undefined. Okay. What about that one? Let's see if we can do this a little faster now. Sorry, I need to cancel this call. All right. Jackson, you're up. And Jackson, since we've gone through enough of these, and I think I'm starting to bore you all, why don't you just tell us all of it? So I want us to look at what's happening at 0, at x equals 0, not 2 this time. I'm going to switch the x up. So what is the function's value at 0?
So it's undefined.
It's undefined at 0.
You come from the left, you're approaching 1, and you
From-
come from the right, you're also approaching 1.
Okay, so everyone see that. At 0, we're undefined. From the left, we're approaching 1. From the right, we're approaching 1. Good? So do you all agree, like visually, this stuff, I think once it kind of clicks, it's not too bad? Yeah? Okay. Maybe I spoke too soon. All right, this is an interesting function. It's worth talking a little bit about the function itself first. So, Al, I'm interested in what's happening at 0, Al. So, at 0, what's going on with this function?
It's all over the place, is the best way I can explain it.
At 0, though.
What?
Plug 0 in here.
Oh,
What are you going to get?
oh.
It's undefined, right? So algebraically, 0 in, we don't have an answer. So f of 0 is undefined.
So is there a hole that we just can't see?
We just can't see it. Okay? You can't see the hole, but it's there. Now, from the left, Anika? Annika. Which one? Annika? Okay, Annika. I spoke too soon. Okay, so Annika, from the left, I'm going to try and help you out. I'm going to kind of zoom in on this a little bit so you can see it a little better, all right? So I'm going to zoom in. There, does that help? No? Okay, I'll zoom in a little bit more. Does that help? No, doesn't help, does it? So what's happening here is that it's hard to explain this, but this is fundamental for where we're headed in this class. Let's take a look at what's happening to that expression right there, 1 over x. Okay? Let's look at 1 over x as a function, all right? Just as a function. This is one of the ones we should know, right? One of our toolbox functions. 1 over x looks like this, and then it looks like this, right? Okay? So let's imagine that we're trying to approach 0 from the left, right? We're trying to come in this way, which first we're gonna try and plug in a number that's approaching 0 here, and what's going to happen to the value of this thing I've circled here? What's going to happen to it? Where's it headed? To negative infinity, right? It's just going to take off. So the way to think about this is, as you try and come in from the left to draw this, the argument of the function, the thing inside, is taking off to negative infinity. And so you're trying to figure out how to graph sine of something that's becoming negatively infinite. So imagine the sine function now, right? Our sine function looks like this. And you're basically, as you approach 0 here, you're trying to graph this function, this direction, all of it, the whole sine function in that direction forever. You're trying to squeeze into this small space. And the closer you get, the more oscillations of sine you start to get. Does that kind of make sense? So this function is just freaking out, all right? So in this case, Annika, coming in from the left, we don't have a value, all right? It's not headed to somewhere in particular, right? Like it's not like going to 8 or going to 6 or going to 4 or going to 1. It's just all over the place. And since it never settles down to anything, we will say that from the left, this limit is a terminology we'll use in a minute. This limit does not exist. That's the answer. That will be the answer. Does not exist. And then what do you think about from the right? Same thing, right? It's trying to squeeze all these oscillations of sine into this tiny little interval, and it can't do it. All right? So this was just more to get you to see, like, these functions can get somewhat weird. All right.
Since it's a sine function, shouldn't it be approaching 0 theoretically? Don't all sine have to pass through 0?
Well, all sine functions where any sine function that looks like that, well, let me do it this way. Let's say I gave you this sine function right there, right? Then I could move it, I could move that would basically either move it left or right. So I could make it where your sine function does not pass through 0 just by doing a translation, right?
Yeah.
Even more here, if the thing in here is not linear, in this case it's 1 over x, then it's very possible that it never goes through 0. Like the sine function will never go through 0. And in fact, you can't go through 0 here because at 0 it's undefined. And as you get closer to 0, this thing just tries to, I don't know if that's helping. Okay. All right, now do you all see some like little jagged edges and stuff in here? This is the computer freaking out. This is not what the graph looks like. The computer is really starting to have trouble graphing this thing. All right? All right, here's one. This is an interesting one. We're almost done with these pictures. Man, we're almost running out of time too. Wow. All right, so we're almost through this thing here. We're on Yusef? Yusef. Man, I should not have said anything. Yusef. And I think I called you last time, right? No? Did I call you last time? No? Okay. Say it again, Yusef? Okay. All right, I'm interested here in what's happening at 0. So can you tell me at 0 what this function is doing? Okay, so if there's no graph, what do we say? Undefined, right? All right, let's keep going. I'll let you have this one. What's happening as I approach 0 from the left? Where's the function headed? What do we call that? Which way? Negative infinity. So it's headed towards negative infinity this way, right? So as you approach 0 from the left, it's headed to negative infinity. And James,
Yes.
what about as we approach 0 from the right? It's headed to positive infinity. So this is an example where at 0, the function's undefined. From the left-hand side, it's headed to negative infinity, and from the right-hand side, it's headed to positive infinity. This one's like really, nothing is consistent, right? Everything's kind of different. All right. Michael? Michael?
Yeah.
Salmo? Yeah. Yes, sir. Okay. Okay, what's happening at 0?
Well, that should be undefined.
It's undefined.
It's not reaching 0 at all.
That's
on
right.
Either side.
Yep.
Because they're within the asymptote.
That's right. So there's an asymptote, so it's undefined at 0. So how about from the left? Where's it headed?
Same thing.
So I'm asking you to ignore what's happening at 0. Now come in from the left. Where is this function headed?
Give or take, somewhere between 10 and maybe negative.
Here's 0. You have to keep getting closer. So you have to keep walking on this graph.
Right.
And it only stops here because I ran out of room. So this thing keeps going, right?
The answer would just be positive.
Positive infinity. So from the left, we're headed to positive infinity. And how about from the right?
Same thing.
Positive infinity.
I don't know why I was trying to give an answer.
It's okay. It's all good.
Sorry.
So this is a little different than the last one, right? Just slightly, though. Slightly different. Both sides go to infinity, don't they? In the middle, it's 0. I mean, sorry, undefined. Okay. Now that we have some general idea, we can start to try and come up with a definition of the limit. So basically, when we find the limit of a function at a point, x equals a, we've been using like x equals 2 or x equals 0. When we're trying to find the limit of a function at a point a, we are inspecting the behavior of the function near that value. near the value. We do not care about the actual value of the function at a, right? So limits means you're talking calculus. Calculus means you're not caring about what's happening at the value. It means what's happening near the value. That means from the left or from the right. Now, when we inspect the behavior of the function, we can approach from one of two sides, right? The left or the right. When we approach from one of these sides, one of the following can occur. So when you're approaching from one of the sides, the function can either approach some number, which in the very first problem, it approached 8 from both sides, right? So everything was great. So we can have it go to a number. We can have the function oscillate infinitely many times, in which case we would say the limit does not exist. Or the function approaches positive or negative infinity, which are like the last two that I explained. Those are the only three things that can happen when you look at limits from the left and the right. It's either going to go to a number, it's going to oscillate and go crazy, or it's going to go to positive or negative infinity. That's it, all right? Remember, we do not care what is happening at x equals a. This is what makes this a calculus topic, all right? If all we did was just say, hey, plug in 2, plug in 0, then we wouldn't be in calculus. Okay, there's one word here that I had bolded that I want to talk about. Near. So this is this word is problematic. So, am I near SeaWorld?
Yes, technically,
Yeah. Okay. Am I near the sun?
It depends on your perspective.
Okay.
Right.
Yeah. This is subjective, isn't it?
Right.
Like, am I near you? I'm more near you than the sun, right? So when you talk about nearness, we are kind of waving our hands a little bit here, because in mathematical terms, near doesn't fly, all right? You can't say, mathematicians don't use the word near. This is a Calculus 1 class. We're introducing the idea of the limit. There is a very precise definition that mathematicians use when we use the limit. And it's something that I'm going to kind of drive around, okay? And the reason I'm going to drive around is the same reason we drive around the imaginary unit, okay? In the imaginary unit, there's just too much there for a student to be able to take in. And if I try and give you the precise definition of the limit, you have to understand logic and proofs. And those are two things that you have no exposure to yet. So how am I supposed to show you the limit definition, the precise definition of the limit, if you don't know what any of it means? I'll put it on the board just so you see it, okay? Just so you can see it and understand why I'm not going to talk about it. What I'm saying is that word near, we're all just going to not ask questions. Okay? Near means getting close, right? And we're just going to all say that's okay, and no one's going to be like, well, near, technically, you could get closer. We're not going to say that. Because, and this is why. Whoa, that red wants to stay. Okay, so to say, this is the precise definition. You don't need to write this down. To say the limit of a function f at x equals a is equal to some number L. So remember in the first example, the limit, we came in from both sides and it was going to 8, right? So this is like, to say that the limit of a function as we approach 2, as x at x equals 2 is equal to 8, right? Means I'm debating how I want to write this. Do you want to see it the way it's written, like mathematically? Yeah. Okay. For every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. That's the precise definition of the limit. So there's a lot of things you would look at this and you would probably have a little bit of an issue with. I mean, first of all, the upside down capital A. I mean, unless you've seen some sort of set theory and logic, then you might have trouble with these we call these like universal quantifiers. How many of you have done stuff with that? Right? So if I start asking you to do problems using this limit definition, do you get what I'm saying? Okay? So I think this is valuable if you're going to move on and be a mathematician or get into the field of mathematics, then you will have to, that will become an entire drawer in your toolbox, of several drawers in your toolbox of learning how to do proofs and how all this language works, all right? So for us, this is the part, when we say near, this is the part that's getting us a precise definition. This is like, if you're close enough to 2, right, then the function will be close enough to 8. Okay, but there's more to it than that, all right? So if you're okay with that, we're going to move past it and we're going to just accept that kind of very loose definition with near in it, okay? Now, if you want to see this more, you can come to my office and I can sit down, I can draw you some pictures and we can talk about it, and that's fine, but it's not going to be here, okay? All right, so blah, 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 blah. Okay, the general idea of the left and right hand limits. I have 3 minutes. Okay, as we discussed, as we approach A, we can either approach from the left or the right. When we approach from the left, we call it the left hand limit. Obvious, yes. And we approach from the right, we call it the right hand limit. So these are like terminology. Now some notation. You ready for some notation now? Like if I say, if I want to give you a graph and I want to ask you, like, what's the limit, like as you come in from the left and the right, I'm not going to write that all in words. I'm going to be like, hey, give me the limit from left. No, I'm going to just use some notation, and here it is. So this is notation we use right here. I'm going to write it a slightly different way right here. Limit, so LIM, x approaches A with the little negative sign, and then f of x equals L. So what this is saying is that you're taking a look at this graph, right? This function f. You're going to be approaching, let's say, 2. And that little negative sign doesn't mean negative 2. It means from the left side, because aren't the negatives over there? Okay, so you're approaching from the left side. And when you look at that picture and you come in from the left-hand side, the answer is L, or maybe it's 8, or it's 6, or it's whatever it is, right? Understand that notation? Okay. So the negative sign is in top right, like a superscript. Now, what do you think the notation for right-handed limit is going to be? Same thing with the little plus sign instead. Okay, so we just change that to a plus, and that means we're talking about a right-handed limit, or a right-sided limit. Okay, and that's coming in from the right. Are the left and right hand limits always the same? I showed you examples where they were, and I showed you examples where they weren't, right? All right. So if you see a little negative up here, it means coming from the left. If you see a little plus here, it means coming from the right. What if your teacher's rude and wants to confuse you and gives you the limit and they don't put a plus or minus here? They leave it out. Then what does that mean to you? Yeah, so this is what this note's saying. If there's no plus or minus in here, that means you have to check both directions. All right? That means you have to come in from both sides. And the only way you can say that you have an answer is if they both go to the same place. All right? Do y'all hear that? Okay, so I know I'm out of time, but I just want to just kind of reiterate that real quick here. Let me go back up to take all this crap out, turn this off, erase this. Okay. What is the limit as x approaches 2 from the left? 8. What's the limit as x approaches 2 from the right?
8.
Okay. What is the limit as x approaches 2?
8.
8. Because it's from the left and right the same thing, right? Okay. What is the limit as x approaches 2 from the left? 8. Limit as x approaches 2 from the right?
4.
4. What is the limit as x approaches 2?
It's undefined.
Does not exist is what we'll say. And I'll finish this up next class, but if you don't have the plus, if you have a plus, it's from the right. If it's negative, it's from the left. If there's no sign, then you have to check both and they have to be the same. All right, we'll continue with that. We are a little ahead now, which that's okay. All right, so you can do your homework for 1, 2, and then you can at least start the homework for 1, 3. On your way out, I'm going to give you a copy of this quiz. I'm not going to collect it. You can take it home. This is what I was going to expect that you did today in class. But I just want you to have an idea of what I was expecting you could do in 10 minutes. Just so you get a flavor of what I would be asking. Let me turn my camera off and I'll answer your question. See, we're done here. Yep.